In this segment, we're going to look at electrical output for different types of solar photovoltaic modules and arrays. By the end of the segment, you should be able to calculate the efficiency of a photovoltaic cell, as well as a module, and evaluate the output of different photovoltaic modules. Let's begin by re-examining the definition of efficiency in a photovoltaic cell. Efficiency is defined as the power out divided by the power in multiplied by 100. For photovoltaics, that's typically measured in units of watts per square meter. As a reminder, a watt is electrically equivalent to voltage multiplied by current. For sunlight, we measure irradiance, or wattage per square meter, using something like a pyranometer. Generally, this is done using a portable power meter or under standard test conditions. If we look at just the cell itself, the length and the width might be as small as 15 centimeters by 15 centimeters. This gives an area of 225 square centimeters. The voltage would be 0.5 volts because the voltage is fixed for a silicon photovoltaic, but the current could be as high as 8.1 amps. Calculating the power output, 0.5 volts multiplied by 8.1 amperes, we see we get a power of 4.05 watts being produced by the cell. Scaling standard test conditions where radiance is 1000 watts per square meter, we get 22.5 watts irradiating the small 225 square centimeter cell. We now have 4.05 watts of electrical output divided by 22.5 watts of irradiance for the cell area. Multiplying by 100, this gives us an efficiency of 18%, which is pretty good. This calculation scales the irradiance to the area of the cell. Next, we'll scale the area of the cell to standard test conditions for 1 square meter. Let's now take this calculation for a single cell and expand it to a whole module as an alternative way to calculate the power and efficiency over 1 square meter. For a module, the area that we consider is the whole footprint of the module, not just the area of the photovoltaics themselves, which is referred to as the active area. Looking at an older solar cell design where cells were circular, an individual cell could be 4.05 watts, like in the previous example, with an area of 225 square centimeters. If we put those individual cells with the same efficiency into a module that contained 72 cells, we would multiply the 4.05 watts by 72 cells, and we would get potential power output of the whole module being 291 watts. All the cells would sum to be 225 square centimeters times 72 cells, or 1.62 square meters. It's pretty large. At minimum, the module is going to be larger than the sum of the individual cell areas, though, because the closest you can pack any circular object with other circular objects is about 91% of its total area. That doesn't even include the framing or other pieces that are involved in the module. This equates to 291 watts per 1.78 meters, or 163 watts per square meter. Dividing that by the 1000 watts per square meter at STC and multiplying by 100 equals an efficiency of 16.3%. The efficiency dropped from 18 to 16.3, or roughly a 9% loss, from the cell to the module, simply because I'm using round cells. The take-home message is that measuring module efficiency needs to account for the area of the module, not just the solar cell. Significant advances were made in the past 1 to 2 decades regarding manufacturing and the shape of that solar cell. Originally, the cell was circular, and then it had a rounded square cell or a truncated circle shape. And then after that, from crystalline silicon, after that, while this increased packing efficiency, there still were small diamond shapes between the cells. Current polycrystalline cells have a square shape, so while the individual efficiency of the polycrystalline cell is still lower than single crystal, they can be packed much more tightly together. So the area of the photovoltaic module is almost equivalent to the area of the individual cell multiplied by the number of cells. This significantly improves the overall module efficiency by area. Recently, larger modules have become much more attractive since there's a larger ratio of active area or PV area relative to the inactive frame area. There are limits on size, however, due to the manufacturing limits, losses due to series connections, and weights that are reasonable for rooftop installers. There are some spacing limits when modules are tilted on rooftops or a ground top system in order to prevent shading from one module to the other. Building code also has limits on module coverage from the bottom and sides of a rooftop. Because the efficiency of the cell compared to the module compared to the array can sometimes be unclear, we simply take the power output of one module and multiply it by the number of modules in the system, or the array, rather than considering the efficiency of the PV system. For example, a cell could be 18% efficient, and 72 of those cells wired in series yield an efficiency of 16.3%. 10 of those modules are spaced according to functional colimits, giving 15% efficiency for the array. This creates confusion and ambiguity, which is why the module power is used, which is rated on standard test conditions, or STC. Now that we've looked at how to calculate efficiency for individual modules and arrays, we're going to look at different wiring schemes in the next segment and how those manifest into different types of IV curves. We'll also look at an additional piece of PV componentry, which is the bypass diode.